Hello, everybody. I'm meteorologist Jeremy Wheeler, and it's time for another edition of WAVY Science Lab. And today we're going to be talking about the heat. Bring the heat, right? We're going to start cooling down pretty soon. We're going to be talking about, heating up homes, things like that. We talked about cooling down a home a while ago, another podcast. But this one's going to go deep into what heat is, versus temperatures. Temperature, the same thing as heat? No, not exactly. It's a little different, but they're definitely related. And so we are going to talk a lot about that today. I'm your host, meteorologist Jeremy Wheeler, and let's get started on what we're going to be doing here. So we're going to do a recap, talk about temperature a little bit. So we did cover temperature before. I admit we're going to do a quick recap. And so temperature, what is it? How hot or cold it is? That's very easy. So it's the average kinetic energy of the particles in a system. So it's, kind of taking a snapshot at how much energy is in the system. And so we broke it down before, but that's basically breaking it down right there. So let's also recap this. Temperature is average kinetic energy. Heat is the total kinetic energy in the system. A little bit different there. And so it also involves the temperature, but involves how much of a substance you have. For instance, this drink may be, very hot, but there's not a lot of fluid in it. But then, versus the ocean or a lake, which has a lot of substance. And so if we heat that up to the same temperature, of course, there'd be a lot more heat in that lake or ocean compared to my little drink here, which does have a lid, by the way, boss. Thank you. Okay, so yeah, I'm in trouble. All right, no, let's take a look at it. So this is the temperature measures the heat, but how well does it represent that heat? So we measure it with a thermometer, and there's different types of thermometers. We're going to talk about a little bit of that. But for bigger substances, use multiple thermometers, right? If you want to measure the temperature of a big area, then you have more and more thermometers. We have thermometers around this area. And so the more you have, the better representation you have of that heat, how hot it is outside. And then the ocean as well. You have buoys out there which measure the heat. So the thermoscope was a long time ago, many, many years ago, simple tube and bulb with water. Galileo was often credited, but he didn't have a scale. And then his friend Centaurio added a scale. But then, it was refined. And so then they had the Celsius scale under Celsius, the metric units, and then Fahrenheit, and it developed English units. That's a finer scale, but that's the one that we use here in the United States. So with a big F there for Fahrenheit. So they use other tools to measure the heat as well. There's a calorimeter, instrument used to measure heat, lost or gained from a physical or chemical reaction. So it's a container, and it's got that reaction inside of it, and it actually can measure the heat inside of it just from that reaction, not from, the substance, of course, is a base. They measure it from the initial, but then after the reaction, it measures the difference in that. Pyrometer. Really cool instrument that measures very high temperatures, forest fires. They can have a pyrometer out there and measure things like that. Buildings, I think, might use that if there is a fire. And then this is going to be really cool. We're going to spend a lot of time on this today. Infrared cameras, right? Predator, seeing the infrared, the body heat, the movie, right? And then all the offsets, Predator 2, all of Predators, all of them. So, right, they used that. And so that made that a little more famous. It was already used, but a little more famous. So this is an infrared image of a dog or an alien. It looks pretty kind of creepy there, actually. But that's the infrared. So an infrared camera takes that. So here's an infrared image of some humans walking, and you can see what we're looking at is the body heat, right? And so the clothing may have some heat to it as well. And so you're seeing these different levels of that. You're seeing these different levels of heat throughout the body, the face, right? Usually a lot of times when you see an image like this, you'll just see like the face and the hands where, the skin is exposed and giving off that heat, and the clothes block it. But sometimes you come from outside maybe, and, it's really hot outside. Maybe those clothes are really hot. And so, it's just you have a varying degree of temperatures in there. And really neat to see. Now, this is night vision. This is a little bit different. This uses starlight, as they say. So you have light coming in. Let's say at night, you can use the light of the stars, literally, which is very faint. And so it can enhance that light. So this is different from infrared. And but I just want to point that out. Sometimes the military can use a combo of the both, or sometimes folks can use a combo. But you can see the personnel there, the military personnel, and it's highlighted at night, probably through their body heat. So here's the electromagnetic spectrum. You've got the really intense radiation, gamma rays, UV rays, right there on the left side, and so there's a lot of energy involved with those. Very short wavelengths. You can kind of see those lines and the wiggles there. So then there's visible. And then there's infrared, which is a longer wavelength, and then microwave and radio are even longer than those. But and you can see the different telescopes, the Hubble and the James Webb and the Spitzer telescopes, how they kind of operate in different ranges and things like that. Pretty neat to see. And that's courtesy of NASA. So and this also courtesy of NASA. Also a breakdown, a little more closer view. So the infrared is considered about 1,000 microns. I read somewhere else it was about 700, but we'll take this and then up to about a little under 1 micron. A micron is 1/1 millionth of meters. So I mean, and then 0.001 millimeters. And a human hair, I thought this was interesting. I thought it'd be bigger, but about 17 microns up to over 100, kind of depending on the person. So that was kind of neat. And then we had the experiment a while back, the temperature experiment, where we added the temperature, right? We raised the temperature in the oven. So really, we're raising the heat. And Frankie, the snowman, had to pay the consequence for this experiment, and so we had the kinetic energy increase, and you can measure that. That's the temperature, the average of it. But in total, we're adding the heat, right? We're adding more and more energy to it, and increasing the heat in the oven, and so we get the temperature of that through the thermometer in the oven. So that's the difference. And again, Frankie, he's got the magic snow hat, so we can bring him back anytime we want. So thank you, Frankie. Thank you very much. You've done very well. Okay, so another example here, real quick, is one that I also talked about, and that was when I made my chicken corn chowder, my world famous. And I said, oh, hey, there's a boiling water. No, that's chicken corn chowder. But the boiling water is right there as well. So, we're adding the heat to that substance. And so the chicken corn chowder pot was bigger. And if we raise that to the same temperature as the water, which it was probably fairly close, then, of course, the chicken corn chowder had more heat because it had more substance to it. It's a bigger pot. And then the boiling water, also a lot of heat in that as well. Let's start that over. And then you contain that heat with the lid, because if you don't, then that heat can escape. And so you get steam coming off, and that creates evaporation. Now we're going to come back and do an experiment here in just a little bit, and we're going to talk a lot more about a whole experiment about heat. All right. All right, we're back, and we're going to talk more about heat now, and we're going to do an experiment, an actual experiment, one that I've done in the past. And we just talked a lot about heat and substance and things like that. So there was our boiling water. So now we're going to set this up, and we're going to talk about specific heat before we get in the experiment. So what is that? The amount of energy it takes to heat up a material to a specific value. And so that's a specific value. And then the heat capacity is the amount of heat needed to raise the temperature of a unit mass of a material by 1 degree Celsius. I know we've been talking about Fahrenheit, but for this scientific units, we're going to talk about Celsius. So there's the units. I don't want to confuse you too much. We're not going to go into this too much. The units are joules, which is energy, per kilogram, right, mass, and then Kelvin, which is the temperature. So that's scientific units. I don't want to get you, but that's just technically what the units are of that. And so you've got the different values here. Air is 1. CO2, carbon dioxide, is 0.84. What does that mean? It means that you don't have to add as much heat or probably energy to the CO2 to raise it to the same temperature as air. Interesting. So it heats up faster. And then aluminum, I thought it was a lower number than that, but 0.9, right? It heats up. But steel, and then steel is 0.46. So it doesn't take much heat to heat up steel. The metal, it gets hot, like on a slide, things like that, a steel slide. And then water, 4.18. It takes a lot of energy to heat that one up. And so the higher the value, the more heat you have to add to raise the temperature the same amount. That's a specific heat. So let's do this experiment. And well, I already did it, but let's take a look at it. And so what I did was I set this up to where uh, the you have five substances: soil, sand, wet sand, water, and air. And then I've got cups. They're all in plastic cups. And there's a heat lamp in the middle of it. And I tried to make it so the cups were all equidistant from that heat lamp. And then, we heated things up and then we took the temperature over a time. So I used a digital thermometer. They were all the same. I got those online. Very cool. I'm going to use those from time to time. And I tried to get it so all the thermometers kind of equalize a little bit. They didn't do it exactly, but they got pretty close. And then I stuck all the thermometer ends, well, the thermometers, into the substance. I try not to put them too far down in there, just a little bit below the surface. Of course, the air was exposed, and that could add to a little bias in the number. A minute more on that in a moment. And then I used a clipboard and wrote things down. And I took a temperature initially, and then every 2 minutes up to 10 minutes. Very cool. I just used the timer on my phone, and that worked out very well. So this was it, and this was the experiment in motion after I turned it on for a little bit. And there you go. There was the clipboard. I started, writing things down, and every 2 minutes, then I would take a reading, and I would just, try and take the reading. I almost had to stop at 8 minutes because it was starting to melt the plastic floor. That's where I do workouts. Sorry, and it started melting the floor a little bit. I was surprised at that. It's a 50-watt bulb. I mean, that probably shouldn't happen, but I mean, it is a heat lamp used for terrariums and things like that. And so anyway, yeah, but so it didn't do it too bad. It just kind of melted a little bit, and I put a little water in the middle, and that was okay. All right, but so we did get the values, and so now we want to take a look at the values of this experimentado, right? So let's get those results and place your bets, right? What do you think would heat up the fastest out of all those? Winner receives a new monster truck. Not really. And I'm talking about the substance, not any people. I don't have a monster truck myself. I can't give it away. Anyway, so here's the results of the experiment. And there you go. Wow. All right. So what are we looking at here? So air heated up the fastest, right? Dry air. It heated up fast, and we saw, the value of it earlier. It was a 1. So it didn't take a lot of energy to heat that up. And it got all the way up above 100 degrees. It did. It was that hot. And then we had the next one in line was soil. Soil's dark. It takes in that energy and the light probably and transfers it all to heat. And so, but it's also dry. It was very dry. And then the next one down was sand. Sand is in the middle, dry sand. That heated fast. And you go to the beach, you hit that sand, and it's hot, right? You're burning your feet on that thing. So so that's makes sense. And then wet sand, that was pretty close to water. It wasn't soaked. It wasn't completely saturated, but it was pretty wet. And so that also took a lot of energy to heat that up. But water, of course, was the other one. It ticks up kind of fast at the beginning there. I think I tried to get the water temperature to cool down as much as I could to meet the air temperature, but it just was taking too long. So so I think initially it just went up that tick there above wet sand because of that. And I tried to zero them out as best I could. So really cool experiment. I've done this before. I think it was at Mississippi State when I taught there. We did this experiment. I think it was Mississippi State. It could have been somewhere else, but as I've taught in several places, it could have been at Virginia Wesleyan University College at the time. But yes, so it's really cool to see the results here. I mean, it's true to life. I mean, you can see it right there, black and white. Just that air heats up really fast, dry air. So if you add humidity to the air, it takes longer to heat that up. It takes because you have to use that energy to heat up that water vapor and water droplets in the air. So that makes sense. That's why on a very humid day you'll probably have clouds, but it takes a long time for that temperature to go up. Whereas if it's super dry or like a desert, it goes up and down really fast. And you can go up and down quite a bit. Whereas the range is much smaller when you have a lot of humid air. So very neat experiment there. And again, this is going back to specific heat. So we added the same amount of heat, the same amount of heat to all these substances equally. I will say the air, though, there was a lot of light, because the thermometer was exposed, so there was light and heat that might have added it. And I tried to keep them the same distance, the thermometers in those cups. So there's probably a little bit of bias in some of this experiment, but I mean, even with a small amount of bias, I think we got a really good reading. We had a really good experiment there. I love doing experiments. Can't do them all the time. Takes a lot of energy and a lot of time and a lot of work, but yeah, it's just really neat to see. And again, times on the bottom and temperatures on the left there. And two substances got above 100 degrees, the soil and the air temperature. So that was really something. That was pretty hot bulb. And then, of course, I was going to do cooling down. I didn't. But if you shut it off, then they cool down also kind of at those rates. All right, we're going to come back now and talk about more real world examples of heat and how it affects us and how we measure it a little bit out in the real world. All right, we'll be back. All right, we're back, and I just want to give a big a round of applause to Mr. Wheeler, who had the successful experiment. Thank you very much. Thank you. Yep. And so, we had the successful experiment. Good job, Mr. Wheeler. Oh, thank you very much. Thank you very much. All right. So let's talk more about the real world now. This was the real world. This does affect you, depending on what kind of substance you have. It affects, even building structures. They have to factor these things in. But now let's talk about clouds. And, so these clouds, there's two types of ways to look at the clouds. You can look at the visible spectrum, which is a different wavelength. And then you can also look at the infrared. So we are actually looking at the infrared, those clouds right there. And here's a different view. So the satellites in space will look down at the Earth and passively take up that energy and figure out where the cloud tops are colder. The brighter the cloud tops here, the lighter it is. The darker it is, the lower to the ground. And so we had some clouds on this day. And so we use the infrared. And so why do we do that? Why don't we use visible all the time? Well, think about it. At night, you can't see it. It's too dark. And so we use the infrared. And then it switches over in the daytime, right? And then it goes back and forth, nighttime, infrared. And sometimes there's an overlap for a little while, after the sun goes down and before the sun comes up, a little bit of overlap. Now, this is an enhanced satellite. This was Hurricane Erin a while back. And so now we're colorizing it to distinguish the higher cloud tops. So the dark reds in here are tall thunderstorms around the eye. The eye, it's dark. Why is that? Well, because the cloud tops are gone. They've sunk. And so that goes down to sometimes the surface. You can even see the surface of the water. And then you have the rain bands and the different greens in there, and that's different heights. But the reds and the dark reds are the tall thunderstorms. The taller thunderstorms, the colder it is, right? Because the clouds go way up high into the sky, and so the taller your thunderstorm, the colder the cloud top. And so those strong storms around the middle, right there, right over there, that's the That's right in that center, and that's what strengthens the hurricane. This is water temperature. Now we're talking about sea surface temperature. Hurricanes need warm ocean water of usually over 80 degrees to form and strengthen. And so on this particular day, we had water temperatures very warm. So it's not just the temperature of the surface. You need a lot of depth. And so, the deeper the warm, if the water is very warm through that depth, then you've got a lot more energy to work with. So in this case, there was a lot of warm water down there around the Caribbean, and the Gulf Stream brings that warm water up along our coast. And so, systems can actually feed off of that a little bit. Now on land, you have air temperatures, and we had temperatures 70s, right? But sometimes you heat things up quite a bit, and you've got to factor in the humidity. So the heat index is, we factor in the heat and humidity combined, and because then it's harder for your sweat to evaporate. It's harder for your body to cool down. And so this is it. Let's say we got relative humidity of 70% and a temperature of 94. So 119 is what it feels like. That's rough. And then, of course, you can use the dew point as well. I just chose the relative humidity in this example. So, for instance, maybe on this particular day in the summer or some day over the summer, you had a high 91, felt like 93, and then the next day, 92 felt like 95, and that heat index can get over 100, and that happens quite a bit. So you have to, and then, if you have temperature below a certain threshold, 85 or 80, I forget, but I think 80, then your heat index doesn't factor in. I had the chart up there, I just didn't look at it, but yeah, your heat index kind of starts at a certain level. So then, you want to stay hydrated if you have, heat index that strong, lightweight, light colored clothing, and check on the elderly, kids, and pets. And so the thing is, we talk about that often about how you should wear lightweight, light colored clothing. Why is that? Well, the light reflects off of the white or the lighter colors, and so the materials, and so it doesn't transfer to heat. But when you have dark colors or black, it absorbs that light and transfers it to heat. So you have the heat from the sun, and you have the light changing over to heat as well. So that's why you wear that lightweight, light colored clothing. It makes a huge difference. It really does. I mean, a big time difference. And then, of course, you have the different heat illnesses in there, heat exhaustion. You get faint, dizzy, excessive sweating. You might have heat exhaustion. I've had that before. I know I have, but I have not had heat stroke. Worked with someone one time. I was doing some roofing in Illinois, and the guy passed out. He might have had heat stroke. We don't know, but he definitely had the symptoms. And all of a sudden you stop sweating, and your fever's over 103. You get nausea, vomiting, rapid pulse. You may lose consciousness. So that's some scary stuff. And then let's talk the opposite end, the wind chill. So the body constantly emits heat. Heat. There you go, the heat. So the heat escapes from you during the wintertime when it's cold. And so, normally you've got a layer around you. You've got kind of a layer of heat around you. But when that wind is strong, it will strip that layer away, and you no longer have that. And so you can get exposure to that cold. And it doesn't apply to plants or inanimate objects. It doesn't work for machines. Not the wind chill. It's us because of that cooling effect. And then you can also get some evaporation if you got some sweat, which you'd be surprised. Sometimes you're bundled up, you would still have some sweat sometimes, even if it's super cold, but it's not as much. And so there. All right, so that's talking about the heat today. We had some really cool stuff. Again, that experiment. Let me back it up before I go to the tip of the day. The experiment, very cool. Again, it's just real world. And you're out there at a beach. You walk on the concrete. It's super hot. The sand is super hot. You get to the wet sand, and it's okay. It's not too bad. And then you stick your foot in the water, which is much cooler, and then you're cooling it down, and sometimes it's even frigid to you. So it's a huge range of temperatures at that beach, and that's why. I mean, this is it right here, right now. There you go, real world examples. And we talked about things like how in the atmosphere, how we measure the cloud tops and things like that. And there's so much more we could go into today. We could go into some space things and how that's measured. We talked about the satellites briefly, but maybe another podcast will do one on just satellites. All right, everybody. I am meteorologist Jeremy Wheeler. I'm your host for today, and hopefully you had some fun and learned something. And we're going to be back with another podcast with new stuff and lots of hot topics coming up. There's a heat reference. Oops. There you go. But hopefully you had some fun today. All right, everybody, have fun. Have a good day. I'm meteorologist Jeremy Wheeler.